Hello and welcome to MT3. We are still on Green's functions, and this time we're going to look at uh, the, the method of Green's functions from a different point of view, using a technique called eigenvalue methods. Now this is described in Riley, Hobson and Benz 17.5 and 17.6, and I will be following the material from here, but you'll also find parts of this explained in chapter 10 in Arfkin, Weber and Harris. Okay, so here's what we're going to do. Consider a Hermitian operator L, a differential operator L. Okay, now if it's Hermitian, then we will know it will have real eigenvalues, that its eigenvectors, eigenfunctions will be orthonormal. So this should be eigenfunctions. Yeah. And the eigenfunctions form a complete basis for this function space. Now I put some stars here. What about degeneracies? And there's a double star here to say that we did not prove that the eigenfunctions of a Hermitian operator in the function space form the complete basis, because that proof was quite involved. We just took it as a given, but these two can be proved, and we also talked about degeneracies when we encountered this issue of orthonormality. But I won't say more about that here. You should know what I mean. You should know by now that all of the eigenfunctions of a Hermitian operator can be made orthonormal. Okay, so that means that if you've got these eigenfunctions yn of x, then L operating on yn of x will give you some eigenvalue lambda n, and that's going to be real, times yn of x. Now this is a particular form of the eigenvalue problem. In Riley, Hobson and Benz they use a generalized form where you have the same kind of expression, except that this should be an x, except that they include a weight function w of x, or they call it rho of x. I've called it w of x in my notes, so this is what we use here. But I won't use the weight function. I'm going to use a standard form. All right. Now we wish to solve this equation. L operates on y to give you f in some range a to b. Now, because this set of functions is infinite set of functions, yn forms a complete basis, let's expand y of x. Let's expand the solution in terms of this basis. So we have y of x is equal to sum. In principle, the sum is an infinite sum, and it could even be an uncountable infinite sum. And this is again described at the very end of chapter 17 in Riley's book. There are situations, in fact it's quite often the case, that this sum needs to be an integral. But for our purposes, we'll keep this as a discrete sum. You don't need these limits really. It's just an infinite sum. So let's just write as a sum there over n. Yeah. Some unknown coefficient Cn, and then we have our basis functions, which are the eigenfunctions of L in here. Now f of x is defined to be the L operating on y, so y is defined in this way, so we substitute, so it's L operating on the sum over these eigenfunctions and these unknown coefficients Cn. L is a linear operator, so we can pull it into the sum, and therefore we get the sum over n Cn, L operating on yn, but L operates on yn to give us, yn is an eigenfunction of L, so we get a lambda n times yn, which is what I've written down here. Great. Now what? Well, now we take the inner product from the left with ym, where m is any other, m is anything. So the inner product of ym with f is the inner product of ym with this entire sum from here. Yeah. Now because the inner product is linear, you can bring the sum outside, and then we have the sum over n, Cn, lambda n, and the inner product of ym with yn. But this basis, the basis of the yns is an orthonormal set, so this is simply delta mn. This is the Kronecker delta. And this collapses the sum onto one case where n is equal to m, and so we have Cm times lambda m, and therefore we have an expression for Cm. Cm is the inner product of ym with f divided by lambda m, and this then lets us write y of x as a sum over n Cn times yn of x. Well, the Cn is given by the inner product which you had. So we have the inner product of yn times f divided by lambda n times yn function of x. This is a number, this is a number, this is a function of x. Alright, now what we're going to do is write down this inner product in its integral form. So we write down the integral there. This is the integral of yn of function of t times f as a function of t, and this whole thing is multiplied by yn as a function of x. Yeah. And now what we're going to do is pull these y's under the integrals, interchange the sum and the integral. Now this can be done if the sum is convergent. So we are making assumptions here. Yes. Now if the sum is well defined and convergent, absolutely convergent, then we can move these things around. So this is what I've done. I pull the integral outside, pull the sum inside. The sum goes over the things which depend on the index n, and that's the yns and the lambda n, so pull them together. So now we have an object which has got a yn star function of t, yn as a function of x divided by lambda n, summed from whatever the range of the sum is. I'm going to remove that range there. And then this whole thing is multiplied by f of t and then integrated over all t. This is how we now define the Green's function. If you remember the Green's function, this is exactly the form of the Green's function, the way we define the solution y of x as the integral of the Green's function times f of t dt. So this stuff over here is our Green's function. It depends on t and x, and it's defined through this eigenvalue expansion as, once again, we don't need this. The reason we don't need these limits is I don't know in principle what those limits are at present. Yeah, so let's not make any assumptions here. So this is going to be the sum over n, yn star of t, yn of x divided by lambda n. It depends on t and x. And that's our Green's function. Great. Now, I have a question here. In fact, we'll address this soon. What if the function f of x is an eigenfunction of the operator L? What will happen? Will our Green's function work? How will it work? Think about it, or work through it. Now, one thing you can see directly from this expression for the Green's function is that g star of x comma t is equal to g of t comma x, or g of x comma t is equal to g star of t comma x. Cool, huh? So if you regard g as something like a matrix of with x in the rows and t in the columns, then g is a Hermitian matrix in some sense. Okay, it's not a matrix, I know that, but it kind of has some nice properties here. The other thing which I'd like you to show, and which can be shown in exactly the same kind of technique as we had above, is that the Dirac delta function, delta of x minus t, is given like g as a sum over n of yn star t times yn of x. And this is the analog of a result we had, I had asked you to prove in finite vector spaces, where the sum I goes from 1 to n of the outer product of the eigen vectors of a Hermitian operator is equal to the identity matrix. And here the identity matrix is taken up by this Dirac delta. Okay, so to prove this, for a fixed t, consider expanding this delta function as some coefficients which will depend on t times this yn of x, and then use the inner product relations as we did it above to find out what these coefficients are. It's kind of nice to do this. Yeah. Okay. Now here's an example of actually using this form of the Green's function in practice. This is taken from Riley's book, so you can have a look at Riley's book to see the problem, but we'll be working through it here with some steps skipped. Okay, so this is from Riley, Hobson and Benz 17.5. Here's your differential equation: y double prime plus 1/4 y is equal to f of x in 0 to pi, and with the boundary conditions y of 0 is 0 and y of pi is 0. And we have two source functions which we're going to work through. So the very first thing you should do is to show that this operator L is Hermitian with the above boundary conditions. Because why do we need to do that? Because the mechanisms we have used here are reliant upon L being a Hermitian operator. It's only when L is a Hermitian operator that its eigenfunctions form a complete basis. Okay, so we need that in here. So show that. Once you've shown that, then we can find the eigenfunctions of L and then use them as the basis. So we want to solve the eigenvalue problem. L operates on y to give you lambda times y, or if you put in what L is, we have y double prime plus 1/4 y is equal to lambda times y, or y double prime plus, in parenthesis, 1/4 minus lambda, close parenthesis, y is equal to 0. Now this is a second order ODE with constant coefficients, and you've seen this one a million times before, a million plus one actually. And the solutions are of the form sine of kx and cosine of kx, where k is the square root of 1/4 minus lambda. Please check this. So the general solutions of the form a times sine kx plus b times cos kx. You apply the boundary conditions and you show that b is 0. And the boundary condition at pi gives us a times sine k pi is 0, which means k pi is n pi. N is 0, 1, etc. Negative values don't give you anything new. Think about it. So we then have the square root of 1/4 minus lambda is n, or lambda is 1/4 minus n squared. Okay, and for each of those lambda n's, lambda now depends on n, so we'll label it as lambda n. For each of the lambda n's, we have an eigenfunction yn of x, which is equal to an, some constant, which we'll find, times sine nx. To find the an's, we normalize this, and I'd like you to show that an is equal to the square root of 2 over pi irrespective of n. Therefore, we have our eigenvalues and our eigenfunctions for all states. Now we can write down the Green's function using our expression in terms of the eigenvalues and eigenfunctions and eigenvalues, and this gives us a Green's function as 2 over pi, this infinite sum, sine nt times sine nx divided by 1/4 minus n squared. It's kind of cool, right? I mean, this is quite different from what we've been seeing in our previous lecture on Green's functions. We've got an infinite sum here. Now you could have solved this differential using the methods we had learned earlier, and you would get something different, which looked different. But let's go on. So the solution then is y of x is equal to the integral from a to b of the Green's function times f of t dt, and you put that in there, you get the infinite sum of this part of the Green's function times the integral from 0 to pi, that's a and b, times sine of nt f of t dt. So now all that remains is to find out what these integrals are, and then you can find out what the solution is. So for the case f of x is sine of 2x. Now sine of 2x, if you look at this here, the eigenfunctions of this operator are of the form sine of nx. So sine of 2x is an eigenfunction. It's not normalized, but it is proportional to an eigenfunction. It's proportional to y2. And I'd asked you to think about what will happen when the source function is in fact an eigenfunction. Now what we get here is that, I'd like you to show this, is that if you put f of x as sine of 2x in this integral here, you get pi over 2 times the Kronecker delta of n2, which means it's 0 unless n is equal to 2, in which case it's equal to pi over 2. So that goes into our solution. We now have a pi over 2 times delta n2 that collapses the sum, and what we get is this simple expression that the solution is minus 4 over 15 sine of 2x. And I have a question here. Did you expect this? You should have expected it. So if you're working through this with some awareness of what's happening, we should have expected that we'd get a sine of 2x here. Of course, I couldn't have expected this constant, but that follows from the maths. Now, here's a question for you. Use the standard methods, Green's functions methods, or anything to find the same solution. It's always nice to follow up on what you've done. Let's go on though and choose the second of these options. F of x is x over 2. Using the same techniques, we put the f of x here as x over 2, and this, not x over 2, it'll become t over 2 because now it's a function of t, and this is the integral you need to evaluate. And this is given as if n is not 0, it's minus pi over 2 minus 1 to the n divided by n, and if n is 0, it is in fact 0. All right, so please evaluate this, and that gives you the solution in this infinite form, infinite series form. N goes from 1 to infinity. We don't have 0 here because when n is 0, we get a 0 from this integral, and we have this expression, which again looks pretty cool. Now the standard Green's function method gives you the solution in a more compact form as y of x is 2x minus 2 pi sine of x over 2. Instead, here we've got this infinite series, and if you wanted to finish this problem off, if you construct this Fourier expansion of this function, you will get this one here. So what the Green's function method has given you is the Fourier expanded form of the solution you get when you apply the standard Green's function method. All right. Now here's an exercise to finish this with, finish up this recording, this lecture. This is discussed in Riley, Hobson and Ben 17.6. Now in this particular section, they consider a generalized form of the differential equation where L operates on y, and then you have minus mu times y. This is where mu is a fixed constant, and this is equal to f of x. Show that for this particular differential equation, the Green's function is given by something which looks like the one we had before, except that in the denominator you've got lambda n minus mu. And this is valid when mu is not equal to any of the lambda n's. Otherwise the denominator blows up. Now, if mu does approach one of these lambda m's, but is not equal to it for some m, then we get what's called a resonance. And the Green's function is dominated by that one state. Now this kind of happens in real-world applications of the Green's functions. And that's where you start to see real resonances. So as in the pendulum, when you have resonance there, you could have a polarizability blowing up. You could have a molecular system absorbing energy because that's where it's got its resonant frequency, where it kind of is able to absorb and emit easily. And this leads us to a powerful application of these techniques. Now, eigenfunction methods these are the kinds of ways of solving, these are the kinds of techniques that we use in practice when finding Green's functions for real-world problems. Now, we can't find the exact eigenvalue spectrum of most, in fact, of our linear operators, but we can often find approximate eigenfunctions and eigenvalues in a systematic way. And this is what we do in many-body physics, where we use these approximate techniques. And when we have these approximate eigenfunctions and eigenvectors, we can then use these kinds of Green's functions expansions to find our Green's functions for differential equations. Now, you'll find applications of this in field theory, in non-relativistic electronic structure methods. As I mentioned, polarizabilities is one of the things I personally look at for many electron systems. But let's end here. So we've looked at examples of Green's functions using eigenvalue methods. It's quite a lovely, beautiful technique and quite powerful. But what we've done here, it gives you a flavor of what's capable, what these methods are capable of. Thanks for watching.